getting recorded at 2 places today, so we'll see how it goes.
Okay.
So, all of us have you. Hello, everybody. You guys have settled. I think this is your first week of classes, correct?
Yeah.
So let me see your names. Rocky,
My name is Deepak.
Deepak, Sanya or Sunny?
Sunny.
Sunny. Okay. Yes. And yeah, I think I know your names. Okay. Okay. Did you guys have a chance to open the homework? No?
Yeah, but like most of the questions.
Yeah, I haven't. I don't think you're ready to do all the questions,
Yeah.
but still half of them, maybe? Not half, maybe first one?
Yeah.
Okay.
But let's start with some of the questions like 1E.
1E, yes. Yeah. Could you do that? 1E? No.
I tried, but
Okay, so let's start with that. Okay. But before that, let me. So quizzes are due every lecture. Homework 1 is due Monday. Readable? So,
Yeah. I think that comes, that's okay. There is this line, that line's make confusion, but in the video there is not.
yeah,
We didn't get that line, that's okay.
good point. Midterm 1. Okay, so that's and last time we introduced the idea of Kronecker delta symbol and how it can be used for doing scalar product. So let's explore that a little bit more because one of you said you attempted that. If you have A dotted with, or whenever we have a vector A, usually we think of this as A1. Let's have it as E1 plus A2, E2 plus A3, where we understand A1, A2, and A3 as the rectangular coordinates. This is IJK. I wrote it as 1, 2, 3 so that I have a label 1, 2, 3 going after it. If it is always, we are going to be writing it in terms of rectangular coordinates, and that means that we are not worried about polar coordinates or spherical coordinates, cylindrical coordinates. We are always going to be working in rectangular coordinates. Then we can be lazy and just say this is not equal because this doesn't have the information of the rectangular coordinates. So this is AI. So you say A1, A2, A3. It's a set of 3 components that specifies the vector. Then you further go down and say that this is nothing but AI, where I is equal to 1, 2, 3, and it has this nice feature that you can extend this to any dimensions. It could be 5 dimensions and still you have 5 components instead of 3 components. That's a simple idea we are talking about. If you have a scalar product, this is A dotted with B, and that would be the sum over I is equal to 1 to 3 AI BI. The index notation involves the idea that instead of summing this, we have an understanding or a notation that whenever the index is repeated, this will mean a summation. So you drop this summation and say this is just AI, BI. You could have also written this as a summation over m, am, bm, and then you would say this is am, m. In that sense, since it does not depend on what I call this repeated variable, that's called a dummy variable, right? Because I could have used I, j, m, or if there was only one appearing, then it matters whatever is on the left hand side has to match the right hand side. If you replace the left hand side, then you have to replace the right hand side also. So that's called a free index. A Kronecker delta symbol, so that's index notation. Kronecker delta symbol. So it's a delta symbol. Involves delta ij is equal to 1 if I is equal to j and is equal to 0 if I is not equal to j. So that's the simple identity, and you can immediately see that if I were to start with a symbolic representation here, I times m of, let's say, am. If you see this appearing anywhere, you immediately say that I is appearing once, m is appearing twice. So anything that appears twice means it is summed. So there is a summation in here. This is summation m is equal to 1 to 3 of delta m. And if I were to expand this, I have I times 1 am or a1 plus I times 2 a2 plus I times 3 a3. Agreed? But I itself is free. I have a left hand side and a right hand side. So let me say if I is equal to 1, then this means that delta 1m am is equal to that summation. If I is equal to 1, there is a delta 1 showing up, that's 1, and these two are 0. This is 1 2 and 1 3. Whenever it's not equal, it is equal to 0, and you learn that this is equal to a1. If I is equal to 2, this is 2m am, and that's a2. And if I is equal to 3, it's 3m am, that's equal to a3. All this information is there in this equation. What is eventually what you want to pick up is that whenever you have a Kronecker delta coming with another variable, this involves a contraction, and notice delta 1m gave you a1, 2 gave you a2, third one gave you a3. This is equivalent to saying this is ai. So whenever you see this expression anywhere, you can, this is called contraction. It just picks the particular component of a vector. Where that can be used is, if you have a vector a dot b, or not a vector, a scalar product a dot b. This is already, we argued that this is ai, bi, but I can replace one of these ais or bis using the summation notation, and this involves I can put in a ij here times bj. That's also the same. If you want to see this in matrix notation, you can think of this as a transpose of a vector. So that's a1, a2, a3. Delta ij is a matrix, or you can imagine that to be a matrix. And this is b1, B2, B3. That's what this means. Here, this is equal, so let's say equal to A1, A2, A3 times B1, B2, B3. Or it can be imagined like this because the matrix multiplication involves this A1, B1, A2, B2. So whenever you have a dot product, we already have this in a different context. You probably are already aware that it can be thought of as a dot product between column vector and a row vector. And now this is you can introduce an identity in here, and that is all there is in here. When we think of index notation, that is what is going on inside. Any questions here until we want to now talk about cross products also. So let's think of a cross product. So let's say A cross B. In rectangular coordinates, how do you define this? There will be three components to this, correct? So let's call this C. And we want to get the three components C1, C2, and C3. We can explicitly write this. If you have E1 here, that's the first component, that will be equal to the second component of A. So this is equal to A2 times B3. Notice the pattern, 1, 2, and 3. It's a cyclic pattern that is coming up, and then you subtract same thing out. So this is A3 times B2. Swap that out. Then you have a second component here, so that's E2. This is, after 2 is 3, right? So it is A3 times B1, 2, 3, 1. Notice the cyclic order 1, 2, 3, 2, 3, 1. So we are looking at it like this 1, 2, and 3. So that's a cyclic property. And then swap it. So you have A1 times B3, and you have the next component is E3. And after 3 is 1, so it is 1 and B2 minus A2 B1. Which you probably have, this is cross product. You already know how to write this. That's just a way of writing. We want to capture the cyclic property somehow in a symbol, exactly like we did this here. So there is a dot product. So we involve or we invoke a new identity. So this is called a Levi-Civita symbol. And this will have, unlike this being a 2-index notation, notice, maybe I should point out, delta ij here has 2 indices. So in general, it's a tensor. Right, question? No? Any comments? No? When we think of a vector, oh, I have something here. Oh, I erased it. When we have a vector, we are talking about a single index, right, or a free index. A vector has 3 components, so you think of it as having 1 free index. A matrix has 9 components, so then you say it is a tensor of rank 2. This is a tensor of rank 1. This is a tensor of rank 2. You can think of tensor of rank 3 when there are 3 free indices. You can think of a tensor of rank 4 when it has 4 indices. So now we introduce a symbol which has 3 free indices, epsilon I, j, k, and that's called a Levi-Civita. And I'm introducing this to write cross product as using indices. So now, since you have 3, I have to define what these components are, exactly like here. I gave a symbolic representation of all the 9 components. Out of the 9, 3 are 1 and 6 are 0. Right? 3 of them, there are 9 components, 1, 2, 3, 4, 5, 6, 7, 8, 9. Out of them, 3 are 1 and 6 are 0. So I explicitly wrote it in this form. Similarly, here, how many components will be there in 3 dimensions? So it is 3 times 3 times 3. So there are 27 pieces to this, and I have to tell you what those 27 pieces are. So here is how I will write it. This is going to be equal to plus 1 whenever the 3 components are cyclic. So if ijk is 1, 2, 3, or 2, 3, 1, or 3, 2, 1.
3, 1, 2.
Oh, 3, 1, 2. Thank you. 1, 2, 3, 2, 3, 1. Yes. Very correct. 3, 1, 2. Right? Yeah. Thank you. It's going to be minus 1 if I were to switch any one of this. So or swap any one of this, if ijk is of the form is, let's say, let me start with 2, 1, 3, and then I again cycle it. So it is 1, 3, 2, and it is 3, 2, 1. Each one of this, if I swap 1 and 2, I get this. If I swap 2 and 1 on the top, I get the bottom one. If I swap 1 and 2, I get the bottom one. Swap means pick one and you replace that. And that will be minus 1. So I said there are 27 components to that. Out of that, 6 are this, and yeah, I suppose. And rest of them, otherwise it's 0. So how many are 0? So 27 minus 6, 21 of them are 0. Otherwise, 0. So these are 21 components. Yeah, I can list them, right? Why not? So list all of them. 1, 1, 1, it's 0. Notice whenever they repeat, that's 0. So it is 1, 1, 1, help. 1, 1, 1, 2, 1, 1, 3. And now I start again, right? So 1, 2, 1, 2, 1, 1, 2, 2, 1, 2, 3, 1, 3, 1, 1, 3, 2, 1, 3, 3. Right? So that's 9 of them. Oh, one of this probably is somewhere here. No. Which one did I miss? So this cannot be there, right? Yeah. So I remove this, 1, 3, 1, this one also, right? Mm-hmm. Okay, so 1, 2, 3, 4, 5, 6, 7 are remaining. If I do this with 2 now, start with 2, again I get all of them, and I'll get another 7, and they are all 0. So let me, again, just for completeness, just write this down. So 2, 1, 1, 2, 1, 2, 2, 1, 3, but I have to remove that. And then you have 2, 2, 1, 2, 2, 2, 2, 2, 3. And 2, 3, 1, 2, 3, 2, 2, 3, 3. And this one. So 7 here, 7 there, and 7 more. So 3, 1, 1, 3, 1, 2, 3, 1, 3. This has to be removed. And 3, 2, 1. Sorry, this has to be removed. And 3, 3, 1. Is that clear? Right, 21 components are 0. 3 are plus 1 and 3 are minus 1. That's the Levi-Civita symbol. You usually just say otherwise, you never list them like this, but at least once you have to convince yourself that there are 27 components and those are the ones that we are talking about. In terms of this, can we write the above vector product? So C is equal, so is this visible then? Okay. So C is equal to, oh, let's say C1, right? Let's just concentrate on C1. C1 is equal to A2 B3 minus A3 B2. I propose that this is actually equal to, let's try, what is 1, 2, 3, C1 JK and AJ BK. Right? This is index rotation now. Now it's good to practice it there. So let's use this. So let's randomly I'm writing an expression. This is IJK AJ BK. The claim is that this will be the cross product. Is this a vector or a tensor, or if it is a tensor of what rank? Is this a scalar, vector, tensor?
Scalar.
It's a scalar.
It has one free index, so it'd be a vector.
Good. So it has one free index. So how many free indices? One, and that is I. Right. And how many dummy indices?
2.
So it is 2 dummy indices, that is J and K. We don't care for the dummy indices. Dummy indices can be replaced with anything else. So if there is only one free index, it's a vector. So whatever this quantity is, it seems like it is built out of a tensor of rank 3, another vector, but eventually it is just a vector. So if it's a vector, there is a free index of I. Let's calculate the 3 components of that vector. So let's calculate what happens if I is equal to 1. If I is equal to 1, I get epsilon 1 jk aj times bk. I'm subbing over j and k, so I sum them over, and so this is 1. I'm summing over j now, so j can take 1 a1 and bk plus epsilon 1 2 k a2 bk and plus epsilon 1 3 k a3 bk. Is that clear what I did? Whenever I see a doubled index, I have to sum it, so I summed over j. But after I sum over j, there is a summation over k remaining. So there is few more sums there. But before I proceed, let me see if this is going to survive. 1, 1, right? Whenever, if you notice, this never repeats, right? Indices never repeat in these 3. There is no repetition here, like each one is independent. If ever the index repeats, they are 0. Right? That's another way of looking at Levi-Civita. When I say otherwise, in all this, there is a repetition, 1 is repeating, like at least more than once. So the moment I write 1, 1, it has to be 0. It doesn't matter what k is, 1, 1, 1, 1, 1, 2, 1, 1, 3, all 3 are 0. So that's 0. I don't have to proceed. If I set it to 0 now itself, I save some time because then I don't have to expand this at all, expand this summation. Here it is 1, 2, so k can be different, and it is 1, 3, it can be different. So I start from here now and say it is 1, 2, sum over this. So this is 1, a2, b1 plus epsilon 1, 2, 3, a2, b3 plus epsilon 1, what did I do? 2. I meant this. So this is expanding this, right? So I'm now working on this, and next is this. So this is 1, 3, 1, A3, B1 plus 1, 3, 2, A3, B2 plus epsilon 1, 3, 3, A3, B3. I'm explicitly doing this, but you don't always do it. It seems like it is tedious, you don't really do that. You can observe the pattern immediately. Here it's repetition, that's 0, repetition, that's 0, repeats 0, that's 0. Right? All the ones that are crossed, they are 0 because the indices repeat. The only ones that survives now is epsilon 1, 2, 3. 1, 2, 3 is plus 1. Right? 1, 2, 3 is plus 1. So it is plus A2, B3. And 1, 3, 2 is minus 1. So that's minus A3, B2. That's convenient because this is nothing but A2, B3 minus A3, B2. That's C1. So I've learned that the first component of a vector product can be written in terms of Levi-Civita symbol in this form. You can do this for other components, so quiz, right? So quiz is do this for 2 and show that this is C2 and do this for 3. So at least 2 or 3, you don't have to do this for both. It's up to you. Is the pattern clear what I'm saying? Any comments, any questions there? Is that clear? So in general, we have a vector product A cross B. Not really the vector product itself. Notice when I say a vector, it is not the same as the components of a vector. So the components of this vector, which means that this is a vector and it has the components I. So the first component will be I is equal to 1. Second component and the third component. In this case, I have written it as C. This is equal to epsilon I j k times aj times bk. Okay. So that's the pattern we have recognized. So now how do we use this in different problems? That's how we want to do. Is that clear? Once we have Levi-Civita symbol, that is because of this symmetry properties, if you want, there are two symbols I have introduced, right? Delta ij and epsilon ijk. There is a symmetry property in each of this. Here, if I replace I and j, the symbol doesn't change much. Like if I were to replace ij is the same as ji. Right. So that's called symmetry. It has a symmetry in swapping I and j. But what will happen if I were to swap epsilons? What would this be equal to? Is this equal? So it's not equal.
It's a minus sign.
It is minus sign, correct? Because we said that whenever something swaps there, that changed sign. So this is having a negative sign. In fact, it is not just ji. If I swap any one of them, it will change sign. So this is also equal. So I could have swapped j and k. So this is minus of ikj. and this is equal to, I could have, so I swap j and I here, k, jk, or I and k also, right? So it is minus k ji. So when it is so this is called antisymmetry. So this is symmetry in ij. Here it is complete antisymmetry, because you can talk about antisymmetry in I and j, you can talk about j and k, so there are various antisymmetries available. So you say it is completely antisymmetric. Completely means in any one of them, completely antisymmetric. Okay. Since cross product is written in terms of Levi-Civita, a cross product also should be antisymmetric. And is it? Yes, it is, right? A cross B is equal to minus B cross A. If we swap the vectors, then it changes sign. Vector product is antisymmetric. That's the same idea that we are talking about. Is there anything else that you can think of with something that is antisymmetric? And yes, if you think of determinant of a matrix, so if you have 1, 2, 3, let's say 4, 5, 6, and 7, 8, 9, and if I were to write this as 4, 5, 6, 1, 2, 3, 7, 8, 9, is this the same? What's the connection between them? The minus 9. If you swap rows or columns in a determinant, there is a minus sign. Right? Every time you swap it, this can be 1, 4, 7, 3, 6, 9, and 2, 5, 8. Right? That's also, so anytime you swap a column or a row in a determinant, there is an antisymmetry. And exactly like the antisymmetry of the Levi-Civita symbol, there are many antisymmetries. You can swap two rows. These two rows, there are 3 possibilities in swapping columns. There are 3 possibilities in doing the rows. So there is a lot of antisymmetry in there. In fact, that leads us to a property that connects Kronecker delta and the Levi-Civita symbol. This has to be seen by swapping each one of them. This is antisymmetry, so I'm not going to be proving it. It cannot be like it has to be verified instead of proving. So the idea is, if you have 2 Levi-Civita symbol I, J, K, and let's say epsilon, L, M, N. Is this a scalar or a vector or a second rank tensor? How many free indices? All are free. So it is 6 free indices. Dummy indices? 0. So if this is a tensor, this has what rank? It's the 6th rank tensor. How many components will it have? So 3 raised to 6. Right? So it will have 3 raised to 6 components. That's a lot of components. But they all can be put together in the following form. So they have this property that this is an identity I am writing. This can be written in terms of Kronecker deltas. Notice how I'm writing I, L, right? First one with first one, and delta I, M, I, N. Right? So it's a very simple pattern. J, L, J, M, J, N, and delta K, L, K, M, K, N. So that's an identity. So every time you want to so there are 3 raised to 6 components, 9 into 9, 81, 81 into 9 components. Any one of them you can calculate it using that. Tedious, but it is useful. Most often we never have this 6th rank tensor appearing. It is usually not very common that you will really encounter a 6th row. What happens is that you want to contract something, one of them is contracted. So let's contract I and L. Right. So I'm setting I, L, and together, so there is a summation in that. So let's say this is I, J, K, and L now is, sorry, this is I, M, N. How many free indices in it? 4 free indices. How many components will it have? 81 components, right? Yeah. But more importantly, it is a fourth rank tensor. So maybe I should write that. So this is 4th rank tensor. So I can put this in, correct? So the only difference is I just have to replace wherever L shows up, I have to write I. So this is I M, I N, delta J I, J M, J N, and delta K I, K M, K N. Wherever there was an L, I replaced it with. How much is delta I? Is this a scalar or a vector or a tensor? Scalar. If it's a scalar, it must be a number, probably. How much is this? 1?
3.
Is that 1? Someone says it's 3. Why is that 3? Why would it be 3?
If there is summation, that would be 3.
So it is summation, right? We agreed upon that if it ever repeats, it has to be summed. So it is repeating. So this is 1, 1 plus 1, 2, 2 plus 3, 3.
Yes, 3.
1 plus 1 plus 1, so that's 3.
Yeah.
Right. So this one here is a number, so I can replace that with 3. Or let me not erase that. So this is 3. Correct? Let's expand this out. This is a determinant, so we know how to do that. So let's do 3 times. Then I have a smaller determinant here, so that's Jm. So I'm doing this times this. So Jm Kn times minus of Km Jn. Is that clear what I did? Okay. Next is I can either go along the row or along the column. Let me go along the column. So I have minus, right, just using the rule for a determinant this time, I have to multiply these two. So that's Im Kn minus of Km In. And finally, plus delta Ki of Im Is that very clear? Okay. We have 4 free indices. That is these two, right? The free indices is J, K, M, and N. Anything else we have to sum over. So this is free, right? J, K, M, N. But now here there is an I showing up, right? So probably I want to contract that if it is possible. So wherever I or anything else shows up, I want to get rid of it if it is possible to. Okay, so let's go with that idea. So let me proceed, and I have the first term, I keep it as it is, so that's equal to 3 times delta Jm and Kn minus of 3 times delta Km Jn. I just copied that out. The next term here is, I will write that explicitly, Ji delta Im and delta Kn. So let's add this Km delta Im. Let me explicitly write it once more, and then I'll process this. Ki Im, just repetition. You don't have to do so many steps. Since it is the first time we are doing this explicitly, but you have to do this in few steps. Okay, so let's do this. There is an I showing up. What is delta Ji times delta Im? That's this term here. The underlying quantity is this. What is that equal to? Correct. Delta Jm. And how do you do that? Whenever there is a delta, and anything that comes with a delta, whenever you contract it, you can swallow that out and rewrite whatever is remaining. So that's Jm. Because this survives only when j is equal to I. So this survives only when j is equal to I. This survives only when I is equal to m. Together they will survive only when j is equal to m. And there is only 2 free disks, is only j and m. So this will survive only when j is equal to m. That is the idea of a Kronecker product with j. But is that clear? Whenever Kronecker delta comes in with any other quantity, it could be Kronecker delta itself, you just swallow that index and replace it with whatever is left out. Is that very clear what that is? Any questions on that? Right? This is a trick. You have to learn that pattern. You have to do this again and again. So if I use that, so wherever I see an I can swallow that, right? So here I see this underlying quantities has this I. Yeah. This will become Jn. Here I is showing up here.
It's a Km.
Km, very good. Right? And here it is I and an I, it becomes Kn. So I'm going to do that and simplify this a little bit. So it is delta Jm, so copy the first line as it is, delta Km, Jn, and this one is minus Jm, Kn, and here it is plus. Let me write Km first, and it is Jn. And do the same thing here, it is plus Km, Jn, minus of delta K, let's say
Kn.
Kn.
Yeah, let me write Jm first so that it looks pretty much like this. Yeah, thank you. Right. And you see that these 3 terms are the same. So 3 minus 1 is 1. So it is J, Jm and Kn minus of if you want Km and Jn. And that's equal to epsilon ijk and Imn. Notice the pattern. What is the free index? It's j and k and m and n. You write j separately in the deltas, and in that same order, whatever comes in that order, you write m and n also. And then you swap one of them. Right? That's what is that identity. You will see this coming again and again. I will immediately do this for double cross product, and that's the first time you will see it, but this will be an identity you will see again and again. This one is very, you will rarely see this coming in that a 6th rank tensor is not common. But this one you will see a lot. Right? You will see this coming. You started with a 6th rank tensor, you contracted one of the indices, you became 4th rank tensor. If I contract this again, you will get a 2nd rank tensor, right? Let's contract the second one. Let's make M as J. So this is epsilon I J K and epsilon I J N. Right? I contracted the J, which is basically I'm summing over. This is, what's the rank of this tensor? How many free indices? Two free indices. How many dummy indices? 2, right? 2 free indices, 2 dummy indices. So it's a 2nd rank tensor. And if I had to evaluate this, I just have to replace M with J in the top expression. So M with J, so that's JJ Kn minus of what am I doing? M with J, right? So it is M with J, so K delta J N. What's the first term equal to? What is delta JJ? 3, right? Because it is 3 terms contribute there, so that's Kn. And what's the second term equal to?
Kj, 3 Kj.
No? What is the second term equal to?
We have J common over here. We can write a del K.
Delta Kn, very good, because this is contracted, right? So you swallow that out and you replace it with Kn. So that's equal to 3 minus 1, so that's delta Kn. So that's a new identity you have. If 2 indices in Levi-Civita are summed, then there's only 2nd rank tensor and it is 2 times that. I'm left out with 2 free indices. I can contract that also. Why not? Do that. Epsilon ijk and ijk. That will be equal to 2 times delta kk. And that's 6. Right? So that's a scalar. So you started with a 6th rank tensor, contracted to get a 4th rank tensor, then a 2nd rank tensor, and you got a scalar eventually. And these all becomes identity now. Right? But you don't have to remember them. But it is good to remember this because this is a little effort you have to put in. Okay? So at least in this course it's good to remember this. But if you're really never using this, at least you can evaluate whenever you want to. This sort of, that's such a nice pattern that you can, you don't really have to remember it. It's sort of always there in your head. So let's use this for some properties of the matrix. Any questions here? How we are? It's just one rule we have used, and that is that whenever there's a summation, I do a or whenever there is a summation, I write II. Right, or there is an implicit understanding that double indices means there is a summation, and we are using 2 symbols, Kronecker delta and Levi-Civita, to process these things. Okay, so let's think of a vector product. A crossed with B crossed with C. Right? What is that equal to? Anyone remembers all of that? Back cab, very good. So that is it. You remember it as back cab. So that means B and C are going to be the free here. So you say this is back, so B times A dotted with C, right? So it is back, and then there is a cab. So it's C and A dotted with B. Okay, so that's correct. So we can derive that. Let's start from, let's say this is D, right? How many indices will this have? Right. If I'm to write that, that's a vector, so it will have 3 indices. So I start with bi. Right. That will be equal. So this is a cross product between 2 vectors. So I write that as epsilon I jk aj times the kth component of b cross c. Is that clear what I did? Because Levi-Civita symbol is used for cross product. So the first thing I can do is, there is a first cross product, I write that. But there is a second cross product. I again do that. So this is epsilon I j k a j, and this is the kth component. So this is k, and I'm going to mislead you guys. So I write it in this form, or D and C right now. So C, I, and J. Is it fine to do that? Do you see any issues with that?
That implies a sum over the i's and j's. Right?
So there is a summation over J and J, and K, and
There's 3 i's.
but there are 3 i's, right? That's a good point. I pointed out last time that if there is one free index, that's good. That means it's a free index. If there is an index that repeats twice, then you sum it over. What if there is an index that repeats 3 times or 4 times? What did I say?
Oops.
That means there is a mistake, right? That's not allowed. So I cannot do this. So it is not clear whether I am summing this or here. So I can never write an index more than twice. So that's a rule. That's a rule of the game if you want, or it means that you're over, or there's an oversight in the rules that you generated, right? Because there is 2 summations, you have to know which one I'm summing. So I have used up I, j, and k. Now the third one, I have to come up with new letters. So this has to be something different. So I say it is m, n. Clear? Right. So I cannot use things again, but here there are how many summations? That is a summation over, so free index in this case is how many free indices? Just I, right? And how many dummy indices? Like I'm summing over j, I'm summing over k, I'm summing over m, I'm summing over n. Right. There are 4 sums if you want. And if you put this together, this is epsilon I j k, and that is epsilon k m n, and you do a j e m c n. Is that clear? Any confusions there? What is this equal to? Now there are 2 Levi-Civita symbols showing up. How many free indices there are? I, j, m, n in this quantity alone, right? Let's talk about this alone. And what will this be equal to? You look at one of the identities there. Notice that I can rewrite this. So this is simply, so I can first swap k and I, or let's just swap the first and third. So it is k, j, I, k, m, n. And then I have a j, b, m, c, n. Seems like I'm writing a lot of steps. That's just because I'm doing it doing very slowly and illustrating it for you guys. Once you get used to this, you can do this in 2 steps. Like at the most 3 steps if you want. What is this equal to? I can go and look at this. Let's see which one is. So notice the first index is repeating, right? So this is I and I repeated. So I have to use this identity, right? J, no. Oh, the upper one. So So that is, this is being contracted. So the first index getting contracted, but the letters are different, but that doesn't matter. I just have to change the letters accordingly here. So this will always be equal to J goes with M. So J goes with M, I goes with N, and then swap it. So J goes with N and I goes with M. Okay, that's the identity. And AJ, BM, CM. Okay. Open this up. Notice that is a Kronecker delta multiplying AJ, J and J contracted. Let me do that explicitly in 2 steps. Maybe it helps. So this is delta IN AJ BM CN minus J gets contracted here and help N gets contracted here, right? So there's N that gets contracted there. Remember, wherever there is a delta, I swallow the contracted terms and write whatever is left. So this is equal to AM that's coming out wrong, right? Did I mess up somewhere? It seems like I messed up. That is a mistake, I suppose. And this is AN, right? J contracts, that's AN, and that is BI and CN, right? And it seems to say that whenever there is a dot product, that's or whenever there is a contraction, that's a dot product. So that's A dotted with B and C. It is minus of, I can move this B and A, so that's BI times A dotted with C, which is the free index gets, so wherever there is an I, that becomes the free index, right? Which is not the identity we wrote. Either we wrote the identity wrong or there is a mistake in there. So let's see, where is the mistake? Oh, when I swapped K and I here, there should have been a minus sign.
Yes.
Correct? So this was a minus sign here. So notice this was a mistake. I forgot the minus sign. Is that clear? Did everyone catch that?
Yeah.
So there was a minus sign there, so this is minus. So that's minus, that's plus. That's minus, that's plus. That's minus, that's plus. Sanya, did you catch the mistake here? Now, any questions here? Very clear. Okay, so let's make a small change in this now. Let's make a requirement here. Let's go back and think of a vector. So a vector is usually, let's say this is 3 I hat, right, plus 4 j hat. That's an example of a vector. 5 times k hat. Let me, here of course we have a1 is equal to 3, a2 is equal to 4, and a3 is equal to 5. Right. And let's have a symbol now. Let's talk about A1 times A2 minus A2 times A1. Notice what I'm doing, I first multiply the first and the second component and then I swap it and I subtract it. How much is that equal to? Say 2, 3. How much is that equal to? Right, that's 1 and 2, so that's 3 times 4 minus 4 times 3. That's 0, right? This is also 0. That's also equal to 0. Whenever you have numbers, they commute. So this is called, I'm going to define an operation which means A comma B is equal to A times B minus B times A. Where do you see that? Where have you seen that kind of operations before? Quantum mechanics, right? And if you have a position x and this is the momentum in the x direction, right? That's a momentum is a vector. There is, let's say this is x1 and that's p1, and what is that equal to in quantum mechanics?
IH.
So it is IH bar. Okay. I is square root of minus 1 and h bar is equal to h over 2 pi, where h is a constant, Planck's constant. How much?
6.6.
6.67? 6.6. I don't remember. I know the h bar actually. Into 10 raised to minus 35, I suppose. Oh, 35 or 34?
34.
34, okay. What is the unit of h? What's the unit of h? What's the unit of Planck's constant? Joule?
Yeah.
Joule seconds.
Yeah.
Joule second.
Is it Joule second?
Yes.
Right. So, and why is it Joule second? Maybe convince me. You can remember this as h bar omega is energy, right?
Yeah.
So omega is frequency 1 over time. So it is. This is Joule. So it is Joule second. What else? Is there anything in classical mechanics that has the units of h bar? Anything in classical mechanics? Of course, h bar is the signature of quantum mechanics, so you would say that that's impossible in classical mechanics. But is there something that has the units of h bar, same units, exactly the same units as h bar? Yeah, I heard that somewhere. Someone was saying.
War.
1. Work. No. Work is joules. Power is energy per unit time, so it's joules per second.
Oh, yeah.
I'm hearing the word, I'm overhearing the word. Someone is saying, what has the units of h bar?
It's not angular momentum, is it?
It's not, no, it is angular. Angular momentum is exactly the, remember, what is the spin of an electron? It is h bar over 2, right?
Okay.
So that's the reason why it has exactly the same unit. So angular momentum has units of h bar. So whenever you think of angular momentum, that must be something, that's the most basic quantum quantity you can connect with in classical mechanics. So it's very fundamental in that sense. So it's x1 comma p1 time is equal to IH bar. What about x1 comma p2?
IH bar.
You never talk about that? Is that how much is that equal to?
IH bar delta 1, 2.
Delta 1, 2, that's 0, right?
Yeah.
right? So it's 0. So in general, if I were to say xi comma pi, how much is that equal to? Or pj. So, right now it is ih bar delta ij. So quantum mechanical relation, the uncertainty relation, or it will be the Heisenberg's commutation relation, can be written as ih bar delta ij. And how can you get that? So if you have a vector a number of course does not satisfy that. Let's have a vector of this kind. So this is sigma 2 times j hat plus sigma 3 times k hat. And sigma 1, sigma 2, sigma 3 are not numbers. These are going to be matrices. And these are called the Pauli matrices. Just as an example, I'm taking that, but it could be any matrices. And matrices don't satisfy commutation relation. Right? If I were to do sigma I, comma sigma j, this is equal to I sigma k now, or let's take that as you say, sigma k. Okay? What's wrong in this? Right away, even if you have never seen Pauli matrices, just based on index notation, what's wrong in this?
You don't have an ij metric, so it's epsilon ij case.
Yeah.
So the statement is whatever is a free index on the left hand side, indices has to match. If there is an I on the left hand side and if it is not dummy, if it is dummy it's okay. If it is not dummy, there has to be a free index on that side. So this cannot be true, right? Sigma k, well, that's a new one. So there has to be an I, there has to be a j. It turns out that this is equal to ij, and since I wrote it as a Levi-Civita, so there is a k there. So I think when Jackson was saying such k, what he meant was that if this is 1, 2, then that's a third one. Right? So, but if it is a free index, you have to respect that. So, often vectors, my here main point is that vectors need not have numbers, right? They can have matrices. What will change in this proof? This is an identity we have, correct? What will change in all these steps we reached here, correct? If I say that A and B does not commute, like I
swap the components down there, you have to include the.
So notice we never swapped the position of A, B, C. We did not swap it here, we did not swap it here. We kept it until here, but at this stage, at the very last, was it the very last stage? Here, right? Here I moved B with respect to A. So let's say that we are doing quantum mechanics and then we are not allowed to swap that. How does this vector identity change in quantum mechanics? This is a classical vector identity. We want to generalize this to quantum mechanics. So let's do that very quickly. So we start again, right? So D is equal to A crossed with B crossed with C. I have 3 minutes. And this is DI is equal. So I go all the way till here, right? Until here I never swapped it. So this is minus AM PM, and this is CI, and plus AN BI CN. And my goal is that I still want to write B in the front and C in the front and rest everything, but whenever I move things, I have to respect the commutation relation. So I have to tell you what the commutation relation between A and B is. So let's say that because I'm going to move let's say B, right? So I want to move here. So whenever I move here, I have A, comma B, right? So let's say AI, comma BJ. What is that equal to? I have to tell you that. And since it's a commutation relation, let's say that this is not anything fundamental because A and J I don't know what it is. But if I were to tell you that this is IH bar times, let's say, M, how many indices there?
0, 6, 2,
There is 2 free index there, so there has to be 2 free index there, right? So I and J, so it's a matrix in general. So if I were to replace this, what I mean here is that minus, so this means AI Bj minus Bj AI is equal to IH bar times Mij. If I want to swap this, I have to take care of that. So this is Bm AM I took it to the right side, so it is plus IH bar times I and J are the same, so it is MM plus A N B I C N. Correct. And I have to keep processing that until I get C on the left hand side and B on the left hand side. So I have to swap this once, and then I get A dot C and an extra term. Here I have swapped, oh, I didn't need to swap this, I was wanting to swap these two, correct? I have to first swap these two and then swap the next. So I did not do that correct, but I'll let you guys do that. I'll stop here. Is that clear for how to proceed? And there is a homework related to that. It's all associated with this. You consider all the vector products and try to do that in quantum mechanics. You should be able to do the homework. I did not finish it here, but I think I gave enough hints that you should be able to proceed. Okay. And don't hesitate to come and ask me in my office if there is any confusion, especially with notations and other things. Okay, good. Thank you. Do you have a class right after this? Okay, so feel free to wrap up.
You're good. It's right there. We have,
Oh, I see, 410.
yeah, we have
So you're
E&M.
not teaching.
No, I don't teach until after E&M. So we are good. I am gonna go get my drink though.